Hi, I am Mohammad Hashibul Haq, 1B of group number 9. Today we are going to present a tiny presentation about our project, which is connection of a large reliable power station with pump hydro storage to an Australian national grid. And this project presentation is submitted to our honorable course teacher, Dr. Nuruttam Das sir. Thank you, sir, for giving us this kind of opportunity. So without further ado, let's get started. Let's start with the introduction part to our project. The This project is aimed to integrate to a 350 megawatt PV farm to 470 megawatt pumped hydro plant to the North Queensland bus through a 440 kilometer and 275 kilovolt coordinator. And this pumped hydro provide peaks load balancing, renewable support, and frequency stability for the Australian national grid. These are the objectives of our project. The first one is model and simulate NEM grid pre and the post interrogation using PSCC software, and we have all know the PSCC software, and we have learned about in our classes. And then the assess voltage and frequency and stability, and to verify the compliance with the NER S 5.2.5 clauses, evaluate the technical, environmental, and economical viability. Statement of methodology. There are a lot of project ingredients, like we have to obtain 350 megawatt PV farm, 470 megawatt pumped hydro, and 440 kilometer transmission line at 257 kilovolt. Both are connected to North Queensland bus. That means it's no load 401, and we have to obtain the system parameter and bus data and perform the base case load flow, and we have to add the PV plus hydro generation and rerun the simulation and compare to another standards and evaluate against the NER standards, and we have to analyze the market and stability effects also. On this slide, we have summarized the key design parameter for different energy storage and conversion technologies considered in our project. Let's start with PHS, or pumped hydro storage. It has efficiency of about 85%, a very long lifeline of 50 years, and relatively low maintenance at 0.9%. The unit cost is around almost $79 per kilowatt hour, making it a natural and cost-effective option for large-scale energy storage. Next, we have CAES, or compressed air energy storage, with a slightly lower efficiency of 71%, a 40 years lifetime, a minimal maintenance at 0.46%. Its unit cost is around 46 per kilowatt hour, which is relatively economical but depends heavily on suitable geological condition. Moving to a HES, or hydrogen energy storage, this option shows a significantly lower efficiency of 42% due to conversion losses. However, it offers flexibility in a long-term storage and transport. The lifetime is around 15 years with a 1% maintenance cost, and unit cost is about 151 per kilowatt hour. Then we have HS, or heat storage, which performs very well with a 99% efficiency, a long 50 years of lifespan, and extremely low maintenance at 0.5%. The unit cost is also very low at 5.8 per kilowatt hour, making it one of the most efficient and more and cost efficient option for thermal application. Finally, we have EBHP, which stands for electrical boiler and heat pump. This system operates at about 98% efficiency with a coefficient performance COP of 3.5, indicated high thermal efficiency. The lifetime is about 20 years, and maintenance is low at 0.5%, and the unit cost ranges from $150 per kilowatt for electric boilers to 870 per kilowatt for heat pumps. That's all from me. I would like to call my next team member to present the rest of the parts.
Hello, I'm Asid Mohammed Shakil Chaudhary. I'm going to present the next few slides on behalf of Group 9. Thank you, Hasibul Haq, for the presentation. I will now cover the result of our load flow analysis. In short, the analysis confirmed two key successes. First, we have seen a clear improvement in voltage magnitudes at the NQ load and CQ load buses. Secondly, by using reactive power control from the PV inverter and hydro excitation system, we have successfully stabilized all system voltages within the target range from 0.95 to 1.05. This directly enhances grid reliability and power equality. Now let's look at the system components that make this project a reality. The core of the integration includes a 350 megawatt PV solar farm and a substantial 470 megawatt pumped hydro facility, which is a combined of two units of 235 megawatt each. To connect this powerful generation to the grid, we are building a 440-kilometer long and a 275 kilovolt transmission line. All of this will ultimately connect to a North Queensland bus or NQ load to our Australian national grid. This slide illustrates the effect of adding the exciter and power system stabilizer. Look at the top row of the graphs. This shows the system unstable responses to a fault without our stabilizing controls. The system oscillates severely, especially when the fault clearance time is longer, as seen on the top right. Now simply look at the bottom row. By implementing the exciter and the PSS, we achieve stronger fast damping of all oscillations. This proves this essential control system provides the dynamic stability necessary to ensure the entire North Queensland system remains robust, reliable, and even under several fault conditions. Moving on, this diagram shows the computational model for our frequency relay. This is a critical protection mechanism based on the work by Vieira et al. In 2006. The relay continuously monitors three key parameters: frequency and terminal voltages. A trip signal is issued only if we hit an overfrequency or an underfrequency condition, and the terminal voltage is below our minimum setting, V minimum. This or and logic ensures that we only disconnect a generation when there is a genuine severe grid disturbance requiring immediate action, ensuring the system security. So now I am going to talking about the NER clauses. This table summarizes our analysis for harmonics acceptability to ensure we are satisfying the NER clauses. We checked a comprehensive range of harmonics against the allowable limit defined by the NER. The key takeaway is the final column, acceptable. You can see that for the third, fifth, and sixth harmonics. The calculated values are initially not okay. They exceeded the regulatory limits. However, these results are based on the early conservative modeling. Subsequent, more detailed dynamics studies, including the finalized filter, confirm that the system will comply with all NER harmonics limits. Therefore, we are confident in achieving full regulatory acceptance.
Thank you, Shakil. So my name is Baitullah Nur Ajam Ridha. Now I will be talking about the study of sustainability. Integrating our energy system helps reduce power losses and ease transmission cognitions, making electricity flow more efficiently. It also increases the share of renewable energy in the national electricity market and lower operating cost by using peak of pumping cycles. So this slide presents a risk assessment for transmission line operations. We identified key hazards such as electric shock, equipment damage, and fall from heights. Each risk was evaluated with an initial score. The control measure like PPE, training and protection systems were applied, though significantly reduces the residential risks. For example, a score of 20 for electric shock was lowered to 4 after control. All safety measures are currently in place, ensuring a safety working environment. This slide highlights risk in PSSE simulations and grid control. Key hazards include system failure and human error during data input, both with an initial risk score of 8. To reduce this, we have implemented measures like backup systems and cross-checkings of data, which bring the residential risk down to just 1. For grid operations, intelligent fault tolerance contractor act as an preventative control mechanisms, enhancing systems reliability. This Gantt chart outlines the timeline of how we have done the project from August to October 2025. So it begins with modeling the Australian grid and gathering journal articles on pumped hydro. We then progress through technical tasks like transmission line parameters calculation, dynamic simulations, and CCT analysis. Midway, we focus on attaching PV and hydro systems to the grid, followed by the exciter turning and harmonic analysis. The final stages involve load rejection responses and compiling the final project report, ensuring the well-structured and timely project completion. In conclusion, integrating PV with pumped hydro significantly enhances grid reliability, stability, and sustainability. It meets NER automatic access standards and plays a vital role in supporting Australian transitions to a cleaner renewable energy future. So there's the references part from those informations taken for our report and for the presentations. Thank you, everyone.